All right. Hi there, folks. I'm sorry that I can't be with you today, but hopefully this will help you um, take some forward steps in terms of what we know about polynomials, and you'll be able to get some good practice. So the first thing is I'm going to have you go along with me and practice identifying the degree and zeros of our various functions. So when I look at a function like p of x, I notice that I've got a quadratic term that is not factorable, and then I've got this linear term, x minus 4, that is squared. And just for right now, I'm going to write that as x minus 4 times x minus 4. Now, if I think about the degree of this function, well, if I were to expand p of x, I would have x squared times x times x. My leading term, or my highest degree term, would be x to the fourth, which means this is a degree 4 or a quartic function. Now, when I think about zeros, well, the only real zero is x is equal to 4, and then x squared plus 9, since that can't be factored, it doesn't have any real zeros, but it certainly has some non-real zeros. For example, when is x squared plus 9 equal to 0? When x squared is equal to negative 9, I can take the square root of both sides, and I see that x is equal to plus or minus 3i. So that would be my two non-real zeros and then my single real zero. What I'd like you to do now is pause and pause your recording and then go ahead and try to identify the degree and zeros of both g of x and f of x. Start back up after you've tried and I will show you my work. All right, welcome back. Hopefully that went well for you, but let's talk about g of x and f of x. Looking at g of x, the first thing I did is I rewrote each factor without the exponents of 2 and 3 there. So I wrote x squared minus 7x plus 10, and then x squared minus 7x plus 10 because it was squared. And then I wrote 2x minus 3 times 2x minus 3 times 2x minus 3 because it was cubed. So now I can see it, if I were to multiply this all out, I would have a highest degree term of 7, x squared, 2, 4, 5, 6, and 7. And then when I look at my zeros, well, x squared minus 7x plus 10 can be factored into x minus 2 and x minus 5. So that gives me zeros, real zeros of 2 and 5. And then my 2x minus 3, each of those gives me a 0 of x is equal to 3 halves. So what we're starting to notice is even though we have something that's degree 7, or like in p of x we had degree 4, we may not have that many unique zeros. Tomorrow we're going to talk about this whole idea of multiplicity and that zeros can be repeated. So for example, as a sneak preview, in this case, g of x, um, the 0 x equals 2 has a multiplicity of 2 because it occurs twice, as well as x equals 5. And then the 0 x equals 3 halves has a multiplicity of 3 because it appears 3 times. And if you add up those multiplicities, 2 plus 2 plus 3, aha, you get a total of 7. Magic? No, mathemagic. All right, let's talk about f of x. It's a quadratic, so sure enough, it's degree 2. Hey, this is where we learn how to factor, or we take advantage of knowing how to factor. This factors to 3x plus 1 and 2x minus 5, so of course it has zeros at negative 1/3 and 5 halves. Um, Now, when things are in factored form, or when they're quadratics, it's pretty easy for us to figure out what the zeros are. But what we want to start being able to look at, and what we're going to need to practice doing, is identifying uh, roots or zeros for functions of higher degree where they might not be in factored form. So if you take a look down at something like h of x, here's a cubic. Um, Off the top of my head, I don't necessarily know what the possible zeros are or what the zeros are. So we need a way to figure those out. And that's where the rational root theorem comes into play. Essentially, what the rational root theorem says is if you have some function, p of x, some polynomial, and its degree n, so that's the highest degree term, and it has a coefficient of p, and then you have its lowest term, its constant, is q, then the possible rational zeros or rational roots, not, this doesn't tell us all what they are, but it tells us the only rational roots that are possible are the factors of q divided by the factors of p. And so this should make sense because if you think about it, if we're to expand a polynomial, then the only way that we can get those consonants at the end have to come from factors of our leading term and factors of our our constant term. Otherwise, the anything that doesn't produce or doesn't come from that list is not ever going to produce our factored form. So that sounds hard to understand, but let's look at an example. If I look at h of x, it's a degree 3 polynomial. My p-value, my leading coefficient is 1. Well, that's kind of nice. And then my q-value is 6. So what the rational roots theorem says is that the possible rational roots are plus or minus the factors of q, which is our constant. So the factors of 6 are 1, 2, 3, and 6, divided by the factors of 1. Well, the factors of 1 are just plus or minus 1. So what this means is if there are rational roots, they have to come from the various combinations of this. So the nice thing here is this denominator is 1, so that means everything over 1 is just going to be an integer. So we could have positive 1 could be a 0, negative 1 could be a 0, positive 2, negative 2, positive 3, negative 3, positive 6, and negative 6. Now, why does that help us? Well, if we're going to find a 0, the best way to do that is to use some synthetic division. And if we can find something that goes in evenly, then we will reduce our cubic to a quadratic. And of course, we have lots of ways we know to find the zeros of a quadratic. We can factor, we can use the quadratic formula, etc. So what I have to do is just try out various possible rational roots and see if I can get one that works. Now I'm going to purposely choose one that doesn't work just to show you. So I'm going to start off with my coefficients, a 1, a 6, an 11, and a 6. And maybe I think, maybe I'll try 2. So is 2 a rational root or a 0? So I go through the synthetic division process, and you'll notice that this is getting way too big, way too quickly, and this is not going to turn out to be, oh, the remainder is not 0, so obviously 2 is not a 0, all right? So I might try a few. You might be thinking, hey, I should probably try something that's negative. So why don't we try something like negative 1? So I'm going to go through the synthetic division process, 1, 6, 11, and 6. Bring down my 1, multiply and add, and so on. And what you notice is, sure enough, I have a remainder of 0. Now, what does that mean? It means that negative 1 is a rational root, which means that when I'm going to break down h of x, one of its linear factors will be x plus 1. Now remember, when I divide like this, what I wind up with is a quadratic. In this case, my quadratic is x squared plus 5x plus 6. So what I did is I divided h of x by x plus 1, and this was my result. But I noticed this is something I can factor pretty easily. So I'm going to go ahead and do that and say, hey, h of x is really x plus 1 times x plus 2 times x plus 3. If I think of h of x as being that, then what are my zeros? My zeros are x equals negative 1, the one that I found here, x equals negative 2, and x equals negative 3. And that's how the rational root theorem, combined with some synthetic division and what we know about quadratics, can help us to identify the zeros or roots of a given function, even when it's of degree 3 or higher. Now it's time for us to practice. So go to the back side of your sheet, and I'm going to start with k of x. I'm going to help you get started, and then you're going to give it a try. So k of x, the first thing I'm going to do is say, all right, if there are rational roots, right, here are my good test values, right? The rational roots, the possible ones, are plus or minus the factors of 2, that's my q value, divided by plus or minus the factors of 4. So the factors of 2 are plus or minus 1, plus or minus 2, over the factors of 4, which are plus or minus 1, plus or minus 2, and plus or minus 4. So what are my possible rational roots? Well, I can start with a denominator of 1. I can have plus or minus 1 over 1, or plus or minus 2 over 1. Now, if I do plus or minus 1 over negative 1 or 2 over negative 1, that just keeps just the same possible signs. Now I'm going to use a denominator of 2. This is going to give me some fractions. Plus or minus 1 half, 1 over 2. Plus or minus 2 over 2 is really just plus or minus 1, so I don't need to write that one down again. And then last, I'm going to use 4 as my denominator, so I have plus or minus 1 over 4, and then plus or minus 2 over 4. Well, I already got those with plus or minus 1 half. So these are my possible rational roots. Now, how do I know which one's going to work? I don't. I just have to try things until I get something that does. Now, sometimes they're going to be the fractions, but oftentimes I start by trying ones that are not fractions. So what I encourage you to do is try to find one rational root that actually works, do the synthetic division, and then when you get down to a cubic, keep going. Try another one. Your goal is to reduce everything down to a quadratic because, again, once we get to a quadratic, we have lots of things we can do to find the roots of a quadratic. All right, so I'm going to have you pause here, see what you can do to find two, remember you have to get it to a quadratic, two roots or two factors that will simplify and break down k of x from a degree 4 polynomial to a degree 2 polynomial. You can do it. All right, how'd it go? The truth is sometimes you get lucky and the first thing you try works, and other times you try a couple things until you finally find something that works. But with a little bit of practice, you will start to notice some things, you'll get better at. Does it need to be positive or negative, and so forth. So notice what I did. I found two roots that worked. The first one was positive 2, and so I did my synthetic division. Now notice I didn't go back to the beginning when I used my second root. I started from right here where it was a cubic, and then I just do synthetic division again. I need to find another root that works. So then I found negative 1 worked. Now I've reduced it twice from a degree 4 down to a quadratic, and this quadratic is 4x squared plus 0x minus 1, or 4x squared minus 1. So if you'll notice here, this shows how I factored k of x into x minus 2 times x plus 1 times 4x squared minus 1. Clearly, my zeros are x equals 2 and x equals negative 1. And then I can solve for when is 4x squared minus 1 equal to 0, take square roots, x is equal to plus or minus 1 half. So sure enough, there are my 4 roots for k of x. What I want you to do is I want you to try g of x. Go ahead and use the rational roots theorem. Figure out the possible rational roots, and then again, your goal is to get from a degree 4 to a degree 2. Now, you may not have used 2 and negative 1 as your 2. Maybe you found that 1 half worked, or you found that negative 1 half worked. And that's fine because no matter what approach we take using synthetic division and quadratics, the roots are the roots. So you and I and anybody else should all get the same answers. So try it with g of x, and then I want you to go ahead and notice that sometimes you may not want to use rational root theorem in synthetic division. Something like k of x, this looks like a quadratic, so I could actually go ahead and factor this. Now you could use synthetic division, and that's fine, but you don't have to all the time. Something like v of x, hey, maybe I'm going to use my calculator. I can graph v of x, and then I can graph y2 equals 0, find an intersection, right? I only have to find one, because I can then use synthetic division to get from a degree 3 to a degree 2.